So in this first question, we're told we have some population, and this population has an average and a standard deviation. So this original population is some distributed data that has some sort of average in it at 2.4 and some standard deviation at 0.7. We don't know how it's distributed. It might be normally distributed. It might be skewed. It might just be chaotic. Because our sample size is more than 30, it doesn't matter what the shape of our population is. We know when we get down to a sampling distribution, we're going to be nice and normal. And remember, when we're talking about a sampling distribution, it's a distribution of sample data. So we're looking at what would happen if we took samplings of size 50 and found the mean for each of those samples of size 50. Each of those samples should mimic the original population, but each of those means will fall fairly close to the mean of our original population. So it should still be centered at 2.4. It will just have a much smaller standard deviation than the original population does. How much smaller? Sorry. How much smaller? Well, smaller by the square root of our sample size. So we're going to take that original standard deviation divided by the square root of that sample size. And that'll give us the standard error for that sampling distribution. Fair? So this one would be centered at the population mean, the average for our sampling distribution is equal to the average for our population. And that standard error is this smaller value, which I'm going to grab. Was it 0.7 divided by the square root of 50? 0.7 divided by square root of 50. 0.099. 0.099. So we're going to add 0.099, so 2.499. If we want one standard deviation up, if we want two standard deviations up, be 2.580-ish. And if we wanted to go down 301 and 2.202, I think, if we want to go that way. So what does this mean? If we go grab or considering grabbing samples of size 50, we'd expect, say, 68% of those to have an average between 2.3 and 2.499. We'd expect 95% of them to have an average between 2.202 and 2.580. And all that stuff from chapter 7 about finding, percentages in different places with z-scores, all of that can be applied to this because it's a normal, nice normal distribution. By contrast, and only a little contrast, mind you, this question here, instead of being given a population's average and standard deviation, this data, whatever it was asking about, only has a proportion to it because this data isn't distributed values. You know, this original population data was a bunch of values that had an average and a standard deviation. This, the original data, was binomial data. All it had was yeses and nos, and specifically a yes at 35% and a no at 65%. So it's a different type of original data. Fair? But if we took a bunch of samples of, in this one, size 80, those proportions that we get, we'd get some that were, you know, nice and on the 35. We'd get some proportions that were a little bit small, some proportions that were a little bit more, but we wouldn't get very many proportions that were far off of that, right? I mean, we might get one that's 0.41. We might get some that are, you know, is it possible to get a point, say 7.2 proportion from a sample of size 80? It's possible, but it's not going to happen very often. If we distribute those sample proportions, we'd expect most of them to be clustered around the 35%, making that 35% the average of our distribution of sample proportions, our sampling distribution. Again, here, the mean of our distribution of proportions is our population proportion. So that puts that at 0.35. And it's going to have a certain sense of spread to it. Now, I can't say that that spread is going to be tighter than the spread of our population data, because our population data doesn't really have a spread. It's just a proportion, 0.35. But how do we figure out what that new spread is in our sampling distribution? Well, that's our formula for it. P times Q over the sample size of 80, that thing's square root. So 0.35 times 0.65 divided by 80, that's going to give us a standard error. Now that standard error tends to be quite small for proportions, only a couple of percent in general. But let's find it. The square root of 0.35 times 0.65 divided by 80. So a little over 5%. So 0.053, I think it was. So that's our standard error, 0.053. So if we wanted to go up one of those, that would be at 40.3% or 0.403. And then 0.456. Go the other way, 0.297 and 0.2. Oh, my brain shut off. 44, I think. I'd use the calculator to get nicer answers for that. But it's still the same kind of idea. We expect, you know, that one standard deviation from the mean should be 68%. So if we go grab samples of size 80, we'd expect the middle 68% of them to be between 29.7% and 40.3%. It would be unusual to get one of these proportions over 2 standard deviations. So over 0.456 would be unusual. So this 0.41 is a high proportion, given that our population is proportions 0.35. So if we found a sample and our proportion of our sample was 0.41, that would be high, but not unusual. that 0.72 is way unusual. So really the difference between these two problems isn't what we're doing with the information. We're taking the information to grab the mean and standard error for our sampling distribution. The difference between these two problems is what our original data looks like. If our original data is a distribution of values, okay, then that distribution of values has an average and a standard deviation, so we can use those to find our sampling distribution numbers. If our original data was binomial data, okay, we can use that proportion to find our mean and standard error for our sampling distribution. So Andrea, you said one of those ones with the curve in the 3 boxes. So I might have over answered that curve in the 3 boxes question. But those are the different, essentially the two different ways that that question can be asked right now. So let me know if that's helpful or if that brought up more questions. More questions.
No, I think you covered it for me.
Micah or Tessa, does that bring up anything else or? Now, one of the reactions that people often have to this section in 8182 is to use these tools to find out about the sampling distributions. We have to know what the either what the mean and standard deviation of the population is, or know what the true proportion of the population is. And in practice, we often don't know that. If we knew the population proportion, why are we going off to find samples if we know what the truth actually is? So we often don't get to use these tools in quite this way. Now, there are uses of these tools, and some of the homework assignments, or particularly in 8.1, some of the problems did kind of allude to some of the ways that these are used in practice. But we're going to be using this tool in chapter 9 to do something quite a bit different than this, but we need this as kind of an underlying theoretical truth to make the stuff in chapter 9 work. Because as I said, usually we won't know what the population values are. Usually what we'll know is we will know what a particular data distribution looks like. We will go out and grab a sample of size 50 and have that sample of size 50. What we will want is we will want to know, okay, what does the population look like? And we're going to get at what the population looks like by telling us what that sample means about our sampling distribution. So we're going to kind of reverse engineer what that population distribution and sampling distribution must have looked like given what one of our data distributions look like. And that's going to bring in some error, some like, well, we're only this sure about it. And that's why our chapter 9 is referred to as confidence intervals. We're not going to be able to find what the answer is because we'll only have one of those little samples. But what we're going to be able to do is find an interval where we think the answer should be based on that one sample. So if you find yourself thinking like, why are we taking samples if we already know what the population looks like? That's a good thing to be thinking. But in chapter 9, we'll see how we're going to use these tools to do that. So are there other things from 8182 that you guys want to look at? Or do you guys want to start talking about chapter 9? I think that homework is due Friday or something. You guys want to go finish up the 8182? You want to start talking about chapter 9? What would be the most helpful for you guys? Just like 20 minutes of silence would be helpful.
I think you pretty much answered all the questions that I was having issues with on the homework. So I think everyone was kind of on the same page with that, because all the ones where I have question marks on them, we just covered it.
Okay. That still begs the question, do you guys want to go finish that up and play with it before talking about 9.1, or do you want to put 9.1 on top of that? And I'm fine either way. We got plenty of time. Either way. And you guys are still being quiet in response to that question. Well, it's only 20 minutes. Why don't you guys go get, can we go on that one? Okay, that's what I like. I like an opinion. So let's start talking a little bit about 9.1. So how is 9.1 going to work? So let's say we have this, nice number line. And we go off and we find a sample. Let's go ahead and use size 50. So we go off and use a sample size 50. Now we know size 50, if it's a distribution of means, size 50 should be large enough to make our sampling distribution normal. So we go off, find that sample of size 50, and the average of our sample of size 50 is, say, 7.4, 7.4 watts. Let's say 7.4 feet. Why are we measuring feet? I don't know. What are we measuring feet? Length of something. Anyway, so of the sample size 50, we go out, we got 50 data points in terms of this number of feet, and we found an average of 7.4 feet. Notice I am back to using the X bar because this is the mean for a sample, right? Up here, this mu was the average for a population, so it was mu. Down here in the sampling distribution, the sampling distribution is a distribution of all possible samples, so it's also a mu. Each of these little data distributions would have their own X bar. And each of those X bars would land somewhere in that sampling distribution. So we are quite specifically going back to looking at that X bar. That X bar is not the true population proportion. We don't know what that is. And it's not the center of our sampling distribution, because again, we don't know what that is. But we're going to put that down here. 7.4 feet. Now, again, we don't know what our sampling distribution looks like, but while it's possible our sampling distribution looks like this, and that sample of that sample of 7.4 is way far away from that hump, it's not likely that it's that far away, right? It's possible that our sampling distribution looks like the green one. It's more likely that it's the green one than the blue one, but it's still, is it likely that we got a 0.74 if that 0.74 isn't under the middle of this curve somewhere? It's likely, if we got a sample of 0.74, it's likely that that 0.74 is somewhere around where that true mean is. Fair? So, okay, we don't know where the true mean is, but that true mean should be near our sample value. So we're going to use the fact that the true proportion should be near our sample value to determine where we think that true proportion is. Now, we could, choice one, this is the bad choice. This is a bad thing to do. We could say, well, our sample was 7.4 feet, so we say that the true mean is also 7.4 feet. Now, the likelihood that our 7.4 feet is exactly accurate, the likelihood of it being precisely true is very, very, very low. It's probably close, but it is very unlikely that we happened to pick the right sample size 50 to get exactly what the population proportion actually is. Does that seem reasonable? This is referred to as a point estimate, by the way. Point estimate. And point estimates are considered to be bad, flawed, problematic. Because just about the only thing we know about that point estimate of 7.4 is that it's wrong. Probably not too far off, but it's definitely not right. So how are we going to get a better idea? Well, we're going to go back to this idea of our sampling distribution. So let's say we have a sampling distribution. That sampling distribution has some average and some standard deviation. Let's make that standard deviation, I'm not actually going to worry about what the standard deviation actually is. But that's one standard deviation, and that's two standard deviations. So we know two standard deviations should contain about 95% of our data, right? About 95%. True? So if we take a random sample, there's a 95% chance that that random sample is in this range, two standard deviations from the mean. The trouble is, we don't know where that true mean is. What do we know? We know where that 7.4 X bar is. Now here's the logic. If this X bar has a 95% chance of being within two standard errors of the mean, then the mean should have a 95% chance of being within two standard errors. Two standard errors of our sample. Let me say that again. If the sample mean has a 95% chance of being within 2 standard errors of the true mean, as given by the sampling distribution, then the true mean should have, or has, a 95% chance of being within 2 standard errors of the sample. Now that's a bit wordy. Let me translate that into a less wordy version. If Bill is within 10 feet of, I don't know, Jan, then, I guess that's Jane, then Jane is within 10 feet of what? If Bill is within 10 feet of Jane, then Jane is within 10 feet of Bill, right? So our 7.4, 7.4 has a 95% chance-ish, about 95% chance, of being within 2 standard errors of the true mean. That means the true mean should be 95% chance within 2 standard deviations or standard errors of our sample. So we still don't know where that peak is, but that peak has a 95% chance of being somewhere close to, somewhere close to that 7.4. How close? 2 standard errors. How likely? About 95%. Tell me how that feels so far. Andrea, it feels yes. A little bit not. Tessa, good. Okay. So we would need to take that 7.4 and we would need to add and subtract about 2 standard errors. That would give us a range, high and low, that we think the mean should be in. We'd have a value and that plus or minus. Usually when we see, data out there in the world, we're often told it's this plus or minus that, right? This is that plus or minus. We just have to be able to calculate or find 2 things. 1, we got to find the standard error. And 2, it would be nice for us to get a better value for how many standard errors we need, a better value than about 2. We've been saying about 2 for a while. It would really be nice for that to be more accurate. Fair? So those are our first couple of goals. Let's handle the standard error first. We know how to find standard error for distribution of means. It's the standard deviation divided by the square root of the sample size. The problem here is that we don't know what the population standard deviation is. Fair? We don't know anything about the actual population. All we know about is our sample. Well, our sample does have a sample standard deviation, so we could use that. Or we might know what our population standard deviation is from some other source. So let's start with that argument. Let's say we know the standard deviation from our population is 1.3. So let's say we're given that from some other source of information. You're quite right. Eventually we won't have that, and we'll need to know what to do when we don't have that. But I'm going to let that happen later. So let's say we can get that from some other source, and we'll find out what that source is later. So that's 1.3 divided by the square root of our sample size was 50. So we can compute standard error. Let's do that real quick. 1.3 divided by the square root of 50. 0.184. So 0.184. So that gives us 7.4 plus or minus, again, about 2 times 0.184. So about 2 standard errors. Okay, now we could use we could use 2, but if we use 2, we wouldn't be able to say 95%. We'd have to say about 95%. And I don't want to say about 95%. I want to say it is 95% likely. I want to say that 95 with an assuredness. Fair? So what I want to know is how many standard errors do we have to go to get that 95 much more solid. So if we want what the actual boundary is for 95%, you guys remember doing this stuff in chapter 7. There'd be 2.5% down there, 2.5% down there. So if we did an inverse normal with that 0.0250, and a mean of 1 and a standard deviation of 0, that would tell us exactly how many standard deviations or standard errors below the mean that 95% is. You guys remember doing that in chapter 7, right? So if I grab that calculator, invert norm, that 0.0250 with a mu, I got those backwards, mu first. So mu of 0 and a standard deviation of 1 is negative 1.9. I'm going to go 1.96 to round that a little bit. So negative 1.96. Now, that's about 2, right? It's just more accurate. Where did the 1.3 square root of 50 come from? Oh, that's our standard error formula. The standard error for a sampling distribution is the original standard deviation divided by the square root of the sample size. So that's that one, and that's the only one up there. So that's the 8.1. So that's a more accurate version of our about 2. If we did the same thing with the 0.9750 invert norm with that, we'd get 1.96. So that plus or minus about 2 standard deviations from the mean for a 95%, this is the more accurate version of that about 2. And we're wanting to get more accurate, so we're going to use that. So the 7.4 plus or minus about 2 is going to be more specific now, 1.96 standard errors, and our standard error was the 0.184. So then 7.4, well, I'm going to find out what this product is first and give you some vocabulary here. That 1.96 we often refer to as the critical value. And specifically the critical value for 95%. So we want to be 95% confident that our true mean is in here. That's the critical value for 95% confident. If we want to be more confident, we'll use a different critical value. If we want to be less confident, saying I only care about being 90% confident, we use a different critical value. That 0.184, that's our standard error that we found by the sigma divided by the square root of the sample size. Together, if we find that product together, that gives us what we call, you'll be familiar with this term, the margin of error. Margin, sorry, of error. So the 1.96 times the 0.184. So 0.360 or 361. So 0.361. That's the margin of error. That's the plus or minus on our approximation. So we went out and found, on a sample size 50, we found an average of 7.4. Well, we know that 7.4 isn't quite right. How off might it be, considering how our population is distributed, the 1.3, given the sample size, 50%, we are 95% confident that the true proportion, or average, is between the 7.4 minus that. So that would be what, 7.0039 and 7.761. So we get a confidence interval, an interval in which we believe to a given confidence value that we believe the true mean to be. It's somewhere in that range. We are 95% sure. So that's kind of an overview of chapter 9. Actually, this is most of 9.1 and 9.1 and 9.2. Okay, we have to learn how to deal with the fact that we normally won't have this population standard deviation. But what are we going to generally use instead? We're going to use the sample standard deviation instead, and we have to compensate for that a bit. So we'll talk about doing that. We have to be able to do this for proportions as well. Well, for proportions, we use the standard error for proportions instead of the standard error for means. Other than that, this is the vast majority of 9.1, is taking this 8.1 sampling distribution and reversing it to find approximations for where the truth is. And we'll spend a bunch of time doing this on Tuesday and Wednesday and Thursday. I think that homework is due Friday. But that's kind of an introduction to what this idea is. It's about finding that plus or minus that we see in so many applications. We often see this, we think the value is this plus or minus this margin of error. Where does that plus or minus come from? This is how that plus or minus is found in practical applications. Tessa, did it make sense where that standard deviation divided by square root of the sample size came from? Good. Is it that, Micah, you said you wanted to start talking about 9.1? This should be a good introduction to that. Anything you wanted to ask about that introduction to that? You guys can actually should be able to take that and start reading that and playing with that. You guys good? Micah, good? Good. Andrea, anything I can do for you before you guys head out?
No, I think I'm good right now.
Okay. Go play with that stuff and let me know if anything comes up.
All right, thank you.
Mm-hmm.